Hiroshima. 20 kiloton, if you will, 20,000 tons of TNT was the strength of that bomb that was dropped on Hiroshima. All right. Very interesting. By the way, my wife said to me, well, there is another problem, dear. If you're claiming that an explosion can happen, then an explosion could not happen from nothing, then the next obvious question is, where did God come from? Is that a fair question? Sure it is. And the answer is, that's correct. In a way, the answer is we don't know. But what we believe is, and this a scientist could say, put his hands on his hips or her hips and say, oh, come on. We believe that God has existed eternally. That is what the Bible teaches. Is that correct? And you could say what caused God, and you can't answer that. So there's always faith involved, isn't there? There's an awful lot of evidence, friends, that there is a God. An awful lot of evidence. All right. Antony Flew. I'm sorry he's not still with us, but for many, many years, he was the most famous atheist in the world. He actually was born in a Christian home. His father was a pastor. But at 15 years of age, he decided there is no God. And during his career, he had a PhD in philosophy. He wrote over 30 books. Very prolific guy. He was from the UK. When you listen to him in a moment, he has an accent. You can tell from where he launches himself on various topics. But he was best known for what argument? There is no God. That's what he was best known for. In fact, those were the debates that he almost always had. There's no God. He was considered the world over as the leading atheist of his time. However, in 2004, he asked an amazing question. Has science discovered God? And here he is. The last book that he published is titled, There Is No God. But the no is scratched out. This is an actual picture of the cover of the book. And in its place, what is there? There is a God. How the world's most notorious atheist changed his mind. And you can see, this is interesting humility, folks. How did he place his picture on the front of this book? Isn't that interesting? He was saying, I am completely wrong. Very fascinating. Now, you can get on YouTube and listen to him tell about this and him being interviewed. This was a little paragraph that was on the book. A British philosopher professor who has been a leading champion of atheism for more than half a century has changed his mind. He now believes in God more or less based on scientific evidence, and says so on a video released Thursday. I can't remember. I think this was in a newspaper from the UK. Now I'm going to play him speaking, and I think we can get it from get it over the PA here. You'll hear someone interviewing him, and then his answers are in white, and the yellow is the interviewee, which is not in the picture. So let's see if we can make it play.
What were some of the factors that prompted you to, in recent years, reconsider atheism and to come to the conclusion that there is a intelligence?
It's been entirely these, I suppose, biological discoveries. The integrated complexity argument.
Now, when you talk about the integrated complexity, is it the unlikelihood of that developing naturalistically, the first complex integrated biological system? Is that where the problem you saw?
Well, yes, because after all, there is a problem about even, well, of physical nature. There's a, if the integrated complexity of the physical world is a good reason, as Einstein clearly thought it was, of believing that there was an intelligence behind it, then this argument applies a fortiori with the inordinately greater integrated complexity of the living world. And it seems to me this is just obvious that that argument is much stronger now.
Could you hear most of it? Yeah. Okay. Changing his course, but it's fascinating that he was willing to be humble enough. Now, there's a word there that I had never heard before. Did you catch that word? Well, I heard that one. A fortiori. I had to look it up. It's just like it's emphasizing it even more, is what the sense of that word is. Now, there are three men facing the camera, and Dr. Peter Robbins on the left interviewing these three. From your left, it's Stephen Meyer. These people all have PhDs, and I think all three of them have more than one. Stephen Meyer has written a couple of books I've read. One is called Signature of the Cell. Anybody seen or read that book? Worth writing down. It's kind of a tomb, but it's pretty good. He's arguing. He's head of the Discovery Institute in Seattle. It's one of these creation research groups. Wonderful guy. You would love listening to him. He's a gentleman and never gets in your face. His second book, I'll think of the name in a minute, released fairly recently. Just an excellent, wonderful fellow. David Berlinski is a Jewish man. And you'll forgive me if I repeat, I think I said this Sabbath, it's not fair. They're smarter than the rest of us. This guy has written a book that I'll tell you about in a minute. I'm going to give you the background first of all. You probably know that Richard Dawkins is the most famous atheist in the world today. He has taken over that position from Anthony Flew. And he wrote a book called The God Delusion. Anybody ever seen it or heard of it? Okay, a couple of people. He's making arguments against the idea that there's a God. He's a very much in-your-face sort of a fellow and is popular because he's clever. And he's plenty bright and quite articulate. But he doesn't really have a mind that says, let's discuss this thing. He's just one-sided. I don't appreciate him very much at all, his attitude. But David Berlinski is actually an agnostic. Now, somebody tell me what an agnostic is. Raise your hand and tell me what an agnostic is.
Doesn't know if there is or isn't.
Yeah, he's a person who is willing to say, I don't know. And that's Berlinski. And in a way, it's fair. God has not made himself provable. Is that fair enough? I said a few minutes ago, there's a lot of evidence that there's a God, right? Of course, if you were a prophet and God gave you visions, I suppose if Nebuchadnezzar were here, what would he say? I know there is a God. And by the way, Nebuchadnezzar has written a pretty significant portion of the book of Daniel. You remember that, don't you? It's not written in Hebrew. It's written in his own language, the Aramaic. But David Berlinski, as a result of the book, The God Delusion, written by Richard Dawkins, wrote a book called The Devil's Delusion. And I have the book, and I'll tell you, this guy is so astute and so deep in his comments. I read one paragraph in that book, and I've got to stop and take a half an hour to figure out, make sure I know what he's saying. You ever read anything like that? It's good stuff. The guy is just so articulate and so deep. Then there's David Gelernter, who recently, I should tell you that he is the head of computer science at Yale. Is that a pretty significant position? It's like there's few people in the world that are as astute as he is. He has become a believer that the universe had to be created by, if in his terms, if you want to call it God, that's fine. This is a remarkable thing, folks. I told you Sabbath that many, many scientists are changing their minds about this issue because of the evidence. And he, for some reason, he's not afraid. He's not. His stature is just too high to be canceled, so he's just wide open. It's interesting to hear him talk, and if you want to write this down, we should have brought paper for all of you to write on. You can get this hour and plus long conversation that Peter Robbins is asking these men on YouTube. If you just put in the three names, Meyer, Berlinski, Gelernter, interview with David Robbins, and it'll come up. It's a little heavy, but I'm going to play you a little section where Dr. Robbins asks David Berlinski about a cell. And I think I can get the microphone back on here. And let me make sure that my volume is up as high as it will go. There, we had a couple of notches. That will help probably. And I'll play the video.
You tell me if I've got it more or less right. In Darwin's time, it was good enough to imagine that the basic unit of life, a cell, was like a little brick of Jell-O. It was an undifferentiated, quite uncomplicated thing, and you could imagine putting many, many, many of them together and getting different forms of life. Is that roughly fair?
I'm sorry, I meant to stop it using the right key. It was distorted there, and we'll play it again. I can't go in the middle of it, but I want what he's saying is, back in Darwin's mind, they didn't even know what a cell was. When Darwin wrote his book, you'll know the book I'm talking about, The Origin of the Species. That's the short name of a long name, the short portion of a long name. We didn't even know what a molecule was. We didn't even know that they existed when he wrote his book. But nevertheless, he could imagine little. In fact, somebody did this. Somebody saw a blob under a kind of a poor microscope in those days, and they thought, well, that's those little blobs. That's what makes animals and people. So that's what Robbins is talking about. And let's play it again, and then you'll hear Berlinski's answer.
You tell me if I've got it more or less right. In Darwin's time, it was good enough to imagine that the basic unit of life, a cell, was like a little brick of Jell-O. It was an undifferentiated, quite uncomplicated thing, and you could imagine putting many, many, many of them together and getting different forms of life. Is that roughly fair? Yeah, it was good enough for Darwin. It's probably good enough for us as well, but it's not true. That's the big problem. The cell is an unbelievably complex bit of machinery.
What did he say? An unbelievably complex bit of machinery. Keep listening.
Unfathomably complex.
What did he say? Unfathomably complex.
And we haven't understood its complexity at all. Every time we look, there seems to be an additional layer of rebarbative complexity that...
I didn't know that word before. Rebarbative? Anybody ever heard that word? I hadn't. It's another one of those words that just means just this expanse beyond belief. Let's keep playing.
Needs to be factored into our theories. Don't forget, the eternal goal is to explain the emergence of this complexity. Yes. And if we're continually behind the curve because the complexity is increasing every time we look, that eternal goal is also receding from view, not approaching, it's receding. It's becoming more and more difficult to construct a theory for that.
Let me just put on the screen the words that he used. Unbelievably. That's a pretty strong description, isn't it? It's beyond belief that there could be something this complex, is what he's saying. And where he's talking about people that are awfully, awfully smart about complex things, right? And he says, unfathomably, we haven't understood its complexity, what? At all. Now, I have a text on biology that I think I paid over $100 for 4 or 5 years ago on my shelf up there above my computer. And it's heavy duty, folks. It's a PhD level course in biology of the cell. That's what it is, cellular biology. And as I'm reading that, it's heavy duty for me. I suppose it would be for you too. And he's saying, even given that tomb of information, we haven't understood it at all. Isn't this amazing? And he says, every time we look, what he means is we figure out something about the cell. And if I get time this evening, I'm going to show you that portion. We figure out something about the cell. Whoa, we're amazed. But then we find that underneath that, there's another huge layer of complexity. And it's like the layers never stop as far as what, modern science has learned. Every time we look, there seems to be an additional layer of rebarbative complexity. The eternal goal was to explain the emergence. Now, here's you probably get this, but let me just clarify this. The scientific community, the unbelieving people of them, believe that somewhere ancient history, maybe millions of years ago, they believe it was many, many, many millions of years ago, like 150, 200 million years ago. There was a pond somewhere that had some primordial substances. That means before there was life. And somehow those chemicals reacted and finally made a cell. And then the cell had enough information then to copy itself and make some creature. And then mutations, we'll talk about that a little bit here in a minute. Mutations that occur, and they do occur by accident. There's no question about that. We'll look at those ideas. And they would believe, first of all, that cell had also had some DNA had formed. It's almost ludicrous. But this is where else do scientists have to go if they don't want to accept a God, see? And that's their explanation of how life began. And what Berlinski is saying here, the goal was to explain how this could have happened. Y'all with me in what I'm describing? How could those chemicals be there? Now, if you have something to write on, this is the arena of what we call origin of life research. Origin of life research. Oh, thank you. There's paper here. If you have a pen, raise your hand and Jerry will give you a piece of paper. Origin of life research. In other words, the research is trying to figure out how life started. That's the idea. And I have two books in my library. Actually, my library is an iPad now. I have 2 books on my iPad that I'm reading at the same time. There's 2 different groups of scientists that got some money, and they are trying to create a cell. And if you want to listen to something very interesting, the chemist that I mentioned to you Sabbath, Jim Tour, like a tour bus, there are scores of videos of him talking about origin of life research. And he gets quite animated because if there's anybody in the world that understands the efforts to make life by these groups, it's this synthetic organic chemist, Jim Tour. And here's what he describes in one way. The groups that are trying to claim that they know how the chemicals hooked up to make a cell, we'll do something quite simple. For example, back in 1953, there were two scientists that put some formaldehyde and some oxygen and a couple of other chemicals in a glass vessel, and they sucked the air out of it, and they put some electrodes in there so they could make lightning strikes, and they let lightning crash into there for about a week. I'm trying to say the name. I think Morley was one of them, but anyway, it doesn't matter. And when they got done, there was a little smudge of stuff in the bottom, and you know what? There were amino acids in that smudge. I wish I had a blackboard up here. I can hardly stand to talk without a, but I guess the church doesn't have a whiteboard, so we'll just try. Amino acids. You all know the word, don't you? They're very simple chemicals that our bodies use. And I'm going to repeat this later. But when you and I eat protein, well, let me back up a step and say, you probably know, but if you don't know, please know it now. All protein is made up of a chain of amino acids hooked together. No exception. And we do not use any protein we eat as it is. Our bodies cut that chain up into pieces. Y'all with me? What are those pieces called? Amino acids. There's hundreds of them in the plant world. We only use 20 of them. You know the names. Lysine, don't you know that word? There's other names that aren't very familiar to us. Scientists, they have to name everything. And they can't just call it thinger number 1 and thinger number 2 and stuff like that. They have to give it lysine and proline and threonine, and all those are all names of amino acids. But it's a very simple chemical, and they're slightly different. And on one end, they have a little thing that makes acid, especially if you turn it loose. And on the other end, they have ammonia. Amino acid. Ammonia acid. You get it? And in between, there'll be 2 or 3 carbons and maybe a side chain or something. So each of them is a little different. And so when you and I eat protein, the protein, first of all, and you know what, Kathy, do we have those sheets here this evening? We won't hand them out right now, but yeah, maybe if you had them ready. So in your cell, in every cell of your body, red blood cells accepted, there is the machinery to build proteins that you and I need, that the cells need. Every single protein your body and my body needs, it makes. Are you all with me? We don't use any protein we eat as it is. Is that clear? I want you to understand that because it has some implications. And after the little machine, it has a name, the little machine that makes the protein makes a chain of amino acids. Oh, thank you for that. I'm all feeling really happy now. Thank you, sweetheart, for bringing the eraser. Then there's another factory. So there's factory number 1 that makes the chain of amino acids. By the way, all of you may not quite make this connection until I describe it, have heard about that happening in the world today. Anybody know what I'm talking about? The vaccine has the messenger RNA. It's actually one side of the DNA, except for a couple of tiny exceptions, that codes for, scientists, they love to use words that we don't understand. That messenger RNA has the information to make the spike protein on the virus. Is this sounding familiar to all of you? Some of you are not nodding. You've got to talk to me with your face, folks. And if it wasn't clear, I want you to let me know. Please? On our own bodies, when your body makes a protein that it needs, when the cell makes a protein that that cell needs, or that cell is going to send somewhere, and that does happen, it creates messenger RNA from the DNA. It makes the messenger RNA that the factories in our cells use. You could say it has a pattern. The scientist would rather say it codes for a certain protein. Do you understand what I'm saying? It has the information. It codes for it. They like to use words that you and I don't normally use. You could use the word pattern. The messenger RNA is the pattern. In the vaccine, it's the pattern to make the spike protein. Are you all clear on the fact that this virus, isn't it funny how these things always dry out? This virus that causes the disease has these little protein portions on them like this. Are you kind of aware of that? That's the spike protein. And the idea is that in our own blood, proteins come along and recognize this and realize that it's foreign, and then the signal is created to have our B cells make antibodies. And the antibodies come along and clobber these things. Y'all with me? So, Robert, what's his last name, the guy that invented this? Some of you will know it. Robert Malone. Thank you, sweetheart. Robert Malone, a man that's been working with vaccines for 35 years. Just a wonderful guy. He's the one that invented this vaccine. He's very much against it now, but he invented the idea. And it's an elegant idea. I got to be careful not to get sidetracked because I've got stuff I want to do besides talking about that. But the point is, folks, that as we'll see a little later, I've got some pictures of it. The way our bodies get proteins, the proteins that your body needs is not from eating them. The protein we eat, we get the individual amino acids, and then our bodies make what we need. And that's all about complexity. So let's take the cell for just a minute. And under a microscope, it looks about like this. And it looks pretty simple. To everybody's surprise, it wasn't as simple as it looked. Here's one little addition. The wall of the cell isn't just kind of a membrane. It's actually a double layer. Are you all with me in what I'm pointing at right here? A double layer. And somebody said, well, okay, that's simple enough. The problem is, it's much more complex than it looked like. Here's another drawing of that double layer. Are you with me on the fact that this yellow layer here is just a little piece of the whole envelope around the cell? You all with me on that? And you can see more clearly here that it's a double layer because the feet don't touch each other from the two layers. And in the wall of the cell are all kinds of different proteins that do thousands of different jobs. And I meant to tell you that the protein chain, I started to say there's another factory, and I think I got sidetracked, that takes the chain and folds it up into a certain shape. Y'all with me on that? Yes. And proteins are able to do a certain job on the basis of the shape that's needed. Got that? How many of you knew that before? Can I see your hands? Good for you, 3 or 4 of you. I often say to the class, and since you're the class today, you have to do this. I often say to the class, proteins work because of, and the whole class says, shape. Are you ready? Proteins work because of their shape. All right. Some of you didn't do it. Shame on you. Unbelievably complex shapes that perform a task that could never be done in any other way. It's just astonishing. Now it gets even worse. besides that little drawing, here's another drawing that shows you how there are two layers. And in fact, I thought I had it on this picture, and I don't want to press it again lest the picture go away. But the little red ball with the yellow legs, that's actually a fat. Do you know what? Does anybody know what a synonym for the word fat might be that scientists like to use, or everybody uses? Yeah. A lipid is a broader category. The synonym for FAT is triglyceride. The word fat and triglyceride are exact synonyms. When a scientist says fat, they're talking about a triglyceride. There are things called monoglycerides and diglycerides. Those are not fat. Are y'all with me on that? Fat is a triglyceride. And so it has three legs. That's why they call it a triglyceride. And two of the legs hang down. Can you see them in the picture? The little yellow legs. And the third leg, in the case of I didn't use this term yet, in the case of the bilipid layer that encompasses the cell. Y'all with me what I'm saying? In the case of the cell membrane, that third leg is got phosphorus in it. It's a phospholipid. And because that is a water-soluble substance, or sometimes we say to the class, a water-loving substance, the Creator designed the phospholeg to be toward the outside of the cell where there's watery stuff, and the two legs that are fatty, which would never work sticking up in the water because they don't dissolve. Are y'all with me on that? Fat does not dissolve in water, correct? So the lower layer is turned over, so the inside of the cell, water works there, and on the outside of the cell, water works there. You got me? This is why there is a bilipid layer that makes the wall of every cell. And it's amazing how tough it is, folks. Every cell of your body is made like this. So all over the skin on my hand, there are those cells, correct? And the bilipid layer is pretty strong, isn't it? I didn't cut myself. It's amazing. This cell membrane, as we like to call it. So it was much more complex, and there are men and women, scientists, that are trying to build a cell from scratch, and they're having a terrible time. But every once in a while, they make a little progress, like the two guys that made some amino acids. And by the way, the amino acids that were made in that experiment were all left-handed. You can't use that in life. You have some that are L's and some that are D's. You could say right-handed if you want, but we usually say L and D. So, and I remember I was in college when that happened, and the newspapers, scientists have discovered life in a test tube. What a joke. They made a few amino acids. And what happens is the newspapers, those guys know nothing about what we're talking about. They're just newspaper people, right? And they expand these claims. Scientists have created life in a test tube, and people write textbooks and tell young kids in school that it's amazing, folks, how there is such a strong lobby, if you will, against what's really going on. But Jim Tour talks a lot about that. You'll enjoy it. Okay. Now, I got to turn my volume off because I'm going to stop and start this, and I don't want his voice. Let me see how I can do that here. I might be able to do it here, but I think I can just do it like this. Let's try that. This is an example of, can you see the bilipid layer there? Everybody? Y'all with me on this? You're not nodding. Are you all with me on this picture? She's not nodding. Okay. Behind you there was a lady that wasn't nodding. Forgive me. And sticking out of the bilipid layer are some proteins. Y'all with me on that? And you'll see it better. There are some proteins hanging down from the layer. You see that? Now, what's going on is we call these things that are sticking out there receptors. You mostly have heard about those things, haven't you? A receptor that's on all of our cells. Many, hundreds and thousands and millions of receptors on any one cell. But these are insulin receptors. And we'll look at this again when we look at the diabetes issue. And by the way, don't miss that. You'll be surprised how many people are at risk for... In fact, you know what the number one risk for Alzheimer's disease is? Diabetes. Number one risk. There's something going on in many people's bodies. They may not get diabetes, but the same thing that's causing it we're quite certain is a big factor in dementia. And nobody in this room, let me say it this way. Every one of us in this room are concerned about dementia, are we not? Sure. Especially because I start to forget people's names these days. Scary. All right. So, I'll just describe this now as it plays. See where it says, whoa, I did it again. At least it wasn't early on. I have to use the K key instead of the arrow. See the little word that came up there, cell membrane. Y'all with me on that? And you see the little yellow dots forming? Okay? They shouldn't be there. But most Americans have them there because of the way we eat. Even if we're not overweight, this can happen. Those are little, well, they're not fatty particles, but that's what they say to the lay people. They're actually fatty acids. Now the legs, the three legs of the triglyceride are fatty acids. That's what those legs are. And so what happens is there's a lot of sugar in the blood, and the body knows that, and it sends some insulin along. See, that's an incorrect thing to say, fat particles, but they do it for the lay people, right? What are they really? Fatty acids. And there's the insulin receptor, and here comes some insulin. The insulin receptor is a protein which works because of its... Come on, you guys. It does work because of its... Yeah. And so when some insulin comes along, it is able to grab it and hang on because of its shape. And actually there's an electrical signature, but I'll try not to bother you with that. That is part of that function. Here comes the insulin, and it hooks up to the insulin receptor, and then a signal. Now this is like a cartoon. It's a chemical thing. But here comes a signal pictured by the artist as a little ball, and that signal will normally bring up another protein that allows the sugar to get into the cell. But because of the fatty acids, that signal is blocked. It cannot get down to that brown thing. Are y'all with me on that? Yes. This is called insulin resistance. You all know the term. Whenever somebody is diagnosed with insulin resistance, what does the physician say to them? I said that wrong. When somebody is diagnosed with diabetes, what does the physician say to them? You have insulin resistance. Now, the physician was never taught this. You can make that go away in 3 or 4 days by changing your diet. John McDougall said recently in a lecture, 100% of type 2 diabetes is preventable or reversible. And we'll look at that. So if I change the way I'm preparing my food and even what I eat, you can remove that excess fatty acids in just several days. And then the signal brings the sugar grabber, I'm using a simpler term, and the sugar can pour in from the blood into the cell. Are y'all with me? What would that do for the amount of sugar found in the blood? It would reduce it to what it should be. And once the sugar is at the proper level, then the insulin quits telling the sugar grabbers to operate. Y'all with me on the idea? I'm just showing you this as an example of a complexity that we have. Now, this is a book written by a friend of mine. He was one of my professors, probably only 5 years older than I am, or was. He's gone now. When I was in college. And how many of you have ever heard of this book or seen it? Interesting. So, Robert Gentry, Creation's Tiny Mystery, in order to understand this incredible proof that the world was created in an instant, I'm going to do some, there he is, picture of him. I'm going to do something up here that I kind of need another table for, but I don't know how I'll do this because I need the screen too. Maybe a piano bench is kind of low. Is there a cart, guys, or a table? I'm sorry that I thought of this just now. Is there another one of these like this? Now, I'm going to give you some nuclear physics for dummies. Are you ready? While they're coming with the table, I'll just tell you this. Some of you know, maybe many of you know, that you and I are made of atoms. Everything that's us is an atom. And the atoms are often hooked together in molecules. That just means several atoms or many, many atoms are hooked together. And when that happens, we say that's a molecule. We don't call it an atom anymore. And most of you have some idea, but we'll learn it if you don't, that in the atom, they're very tiny, but I'm making it big here. In the atom, there's this thing in the middle. We don't have to use the word nucleus. We could just call it the middle. That has two kinds of things in it. It has protons, pink for proton, and it has neutrons. All right? You understand they're much tinier than this. And I think my next slide has what I need. Please don't let this scare you. Up here you have, this is a list of all the chemicals that are found on the earth. Thank you, gentlemen, so much. And there's an exception to that. I think I can get it with one click. The little boxes with chemical names above that arrow are all created by men. Those are not found in the earth. Everything else is found in the earth. And just for fun, there's hydrogen, there's carbon, nitrogen, and oxygen. And if you just took those, even without calcium, you might be surprised. The amount of calcium in our bodies is not all that high. You say, what about all my bones? There's calcium in the bones. But have you ever thought about the fact that if you took a bone that just was taken out of an animal or a person for some reason, it might be kind of heavy, but when you let it sit in the sun for a year, because the water and other chemicals are all gone. So there's not all that much calcium actually in our bodies. If you just took the hydrogen, carbon, nitrogen, oxygen, you would have about 96% of you is made of those four things. Isn't that amazing? There are traces of other things. But I want you to notice something about this box. This box, in fact, don't you all know what percentage of our body is water? The proper number is 60%. And I think, don't all of you know H2O is the symbol, the chemical symbol we use for water? And what that means is you have an oxygen molecule, atom, and you have two hydrogens stuck off at a funny angle here. And that's H2O. Y'all with me on that? Most of you kind of knew that. And that's 60% of you and me. Just those two, hydrogen and oxygen. What I want you to notice about the hydrogen is there's a 1 here and a 1 there. The top one means there's 1 pink. And the bottom one means there's 1 electron. I think all of you know the word electron, don't you? It's a negatively charged particle. You must know what I'm talking about. When you brush your hair and your hair sticks to the brush, we call that what? Static electricity. There's some charges just parked there, right? And don't all of you know that if you have 2 charges that are the same, they push apart. Is that correct? And 2 charges that are opposite pull together. You all know that. If you didn't know it, you know it now. And so let me make it a little easier. Let's go to helium, which isn't in our bodies, but it will illustrate something. That little 2, in fact, in the upper left corner of all of these boxes, that number tells you how many pink ones are in the middle. Got it? And when you take the total weight, which is 4, it tells you that the other 2 are the neutral, equal in weight, and we call them neutrons because they're no electric charge. And the reason the Creator did that is because if these 2 guys are alone in the middle of this atom, what's going to happen? Got it? So the neutrons are there. I can't do this very well. To help keep them together. There's a force there that we really don't understand very well, that these neutrons are able to keep the protons from flying away. Are y'all with me? What do we call this little thing? Generically, what is it? It's the nucleus, or you could call it the middle, right? Now, is this bigger or smaller than the real thing? Much, 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 much bigger. And the way this works is, for every pink one, there is a negatively charged particle flying around. So that when you back up from this thing, it looks like it's neutral. Because you have 2 positive charges, helium, and 2, I don't have another hand. You have 2 negative charges flying around. Are you all with me on the idea? And in fact, these things are flying around so fast that you come up and try to touch this anywhere and you run into one of them. Crazy. So let me use you instead of me since I'm holding. So when I touch this, I'm running into electrons that are keeping me from sticking my hand inside this thing. Are you all with me on this? How many of you are lost? Let me see your hands. How many should have raised their hands and didn't? I'm talking about an atom of helium. Do you all know what helium is? It's a gas. And helium is made of 2 particles that are positively charged and 2 that are neutral, with 2 electrons flying around. That's what a helium atom is. Are y'all with me on that? See? And I know how to kind of talk about this because of the 2 on the upper left, which is 2 of the one on the bottom, the 4 is the weight of the whole thing. Are y'all with me? And 2 of those are the pinks, right? And the other 2 are the neutral ones. That's where the 4 comes from. Y'all with me on that? Now, just for fun, if the protons and neutrons were actually this large, this thing would be out there 6 miles. I was pretending like it was nearby. 6 miles. You may not pick this up, but yesterday I told you that we are 99.999999% empty space. Because every atom, friends, every atom on that chart is like this with more of these in the middle, right? Right? Look up there. Look at the bottom. Look at how many of these pink balls are in uranium. How many? No, the upper left is the pinks. How much? Woo! I don't have that many here. But you get the idea. And if you subtract the 92 from the 238, are y'all with me on that? What's left? 130, 140. Is that correct? Is that correct? So there's 140 white ones to keep all these pink ones from choo! Y'all with me on that? Now, I know that some of you didn't know all this before, but isn't it really some simple ideas I'm showing you, right? And every atom is like this. Mostly space. It's incredible, folks. Mostly space. It's the flying... What did I do with my electron? I'm missing one. Oh, there it is. Yeah, 6 miles away. It's this thing flying around so fast everywhere that makes the atom feel like it's a ball. Y'all with me on that? It's amazing the way the Lord did this. Amazing. And the connection with Robert Gentry is this. When you get enough, see all those pink balls? In fact, let's count them, just for fun. 1, 2, there's 4, 5, 6, 7, 8, 9, 10, 11, 12. What's up there that has 12 pink balls? Magnesium. Are y'all with me? And 12 from 24 is how much? 12. So if I had 12 white balls, let's just pretend they're 12. I don't want to take time to count them. Now they're all interlaced with each other so it doesn't fly apart. Are y'all with me on that? Because of the neutrons. And how many of these would be flying around outside? You got to balance every positive one with a negative one, correct? Are y'all with me? So how many? 12 of these guys are flying around. And all the atoms are like that. It's amazing. And here's the interesting thing. It is the number of pink ones that determines what the stuff is. Got that? You have hydrogen. How many pinks? 1. And you go over to helium. How many pinks? 2. And of course, there's going to be 2 of these because the weight is 4. Y'all with me on that? You understand that the pinks and the whites weigh the same, right? So that's how I know how many whites or neutrons. And I can tell by, we call it the atomic number. What's the atomic number for, let's say, oxygen? Right there. 8. Meaning there are 8. And how many of these? So the whole thing is balanced. Now there are times that you can swipe an electron and now the atom is electrically charged by 1 unit of charge. So, of course, these are way too big. I should look this number up because I did the calculation. And maybe I take just a second of your time to see if I can get to it fairly easily. Where are you, boys and girls? There we go. This is the number of hydrogen atoms to be the thickness of paper. The whole atom, 1 pink and 1 black. Is that correct, hydrogen? You all with me? If this was true size, it would take 8,333 of them stacked That's not one of these, but it's the atom itself. Are y'all with me? The whole atom. It would take 8,000 of those to stack up and be the thickness of a piece of paper. This stuff is tiny, isn't it? And these are even tinier because I was just talking to you about this. Is that correct? See? Now, one other thing I want you to know. And if you promise to come back to Power Night, I will not give you a quiz. If you don't come back, I'll give you a quiz. What have I got here? 2 pinks and 2 whites. What is that? That's helium. I want you to know from now on that the helium nucleus, now there's 2 of these flying around, isn't there? But the scientists have chosen to call the helium nucleus an alpha particle. Would you write that down, please? Alpha particle. These are kind of glued together. Particle. They call that an alpha particle. They call this a beta particle. Anybody in this room ever been scanned for bone cancer? Anybody? How many of you know about a bone scan? Let me see your hands. They take you and they put you on a bed there and they inject into your blood technetium. It's actually up there on that list, it doesn't matter, which is radioactive, which means that in this case, these guys are flying out of the technetium molecule. Y'all with me on this? You know what you've heard radioactive, didn't you? That means a particle is flying out of the atom, and they put you on this gurney, and they actually have detectors lined up all alongside of you that can tell when one of these guys, an electron, whams through them. And it makes an image of the bone. Can you get that idea? And where cancer is growing, because it's destroying bone, the body's effort to replace the bone is amplified, and they see an area of rapid remodeling. What does that mean? Building bone. So this thing doesn't see the cancer, it sees the remodeling that the body is trying to do to stop this destruction. So that's how they detect bone cancer, with a bone scan. And the beta particles are tiny, and they don't cause much damage. So the technician that does this, even though they're wearing a badge to see how much radioactivity they get, they walk around while your body is shooting off these electrons, because the electrons aren't much of a problem. Too much exposure could be a problem, but it's nothing like. See, this electron should be 1/1800 times smaller than this. It wouldn't even be as big as a BB. It would be, I did the calculation, it's just about a tenth of a slice of a BB. This thing should be, if I'm using these sizes here. Y'all with me on this? So the electron, because it's so tiny, doesn't do much damage. But there's quite a few radioactive molecules where these 4 things come out as a piece together. What's this thing called? What do science like to call this? An alpha particle. So we call the radioactive substances, if that's what shoots out, we call them an alpha emitter. Are y'all with me on that? Alpha particles. I'll show you this in detail in a minute. Don't all of you know that radon gas can be a problem? It depends on where you live. But when you get a building permit, I don't know if you built this building or you remodeled this, but when you get a building permit and you're going to put down a concrete floor, you have to, first of all, put pipe down there that's all connected together, and a piece of the pipe finally comes to go outside. Then you have to put washed pea gravel on those pipes and visqueen, and then you put the concrete down. Y'all with me so far? The problem is that radon gas, as you'll see in a minute, is created by uranium, and it comes seeping up through the ground and it goes right through concrete. And in the basement, this could happen upstairs too, but radon gas is quite heavy. So if the basement has a door that gets open rather frequently, the radon gas will pour out the door. Does that make sense? Because it's heavier than air, right? Do you know that 10,000 people die in this country every year from radon gas? And radon gas is an alpha emitter. Alpha particles can't even pass through paper when they come flying out of the uranium or the radon. Are you all with me? So they won't even go through your skin. They won't hurt you, with the exception when you breathe the gas into the alveoli, the little balls in your lung. The tissue there is, the alpha particle is able, because of the soft nature of that tissue, it's able to penetrate that and cause a mutation which eventually will cause cancer. All of the people that die of radon poisoning die of lung cancer. Are you all with me? So alpha particles are not dangerous to just hit me somewhere, but if they're in the air and I breathe them in, if I breathe the radon in and then it shoots out an alpha particle, it can cause cancer. All right. Where is my advancer? Oh, I see it there. I'm only using it to point because I can advance like this, but I got to get back there. So here is what Dr. Gentry did and found. I told you I had to give you a course in nuclear physics so you would understand what his book was about. This is the decay record of uranium. Do you see at the top, U-238? And the first thing it does is send out what kind of a particle? You don't know that that's the Greek letter that looks like that's called alpha. Or do you? Let me make sure you know what I'm talking about. This is the Greek letter we call alpha. Y'all with me? This is the Greek letter we call beta. Y'all with me? So U-238 is radioactive because it shoots stuff out. Are y'all with me on that? And what does it shoot out? No, it shoots out an alpha particle. Right alongside the uranium atom is alpha. Y'all with me on this? And the little down arrow just tells you that when it does that, listen to this now. What makes uranium uranium? 92 of these red guys, is that right? If you shoot out an alpha particle, how many red guys do you lose? Do you remember? What did I tell you this was? A helium nucleus. And what is it called collectively? An alpha particle. Y'all with me on that? This is not rocket science, folks. It's just new to you. Isn't that right? It's not a complicated idea. It's just that you've never heard it before. This is an alpha particle. The scientists just call it that. It's the nucleus of helium, right? And how many electrons are flying around it? 2, because I've got 2 positives and I have to balance it with 2 negative things, see? And so if 2 pink babies leave the uranium, the 92 becomes what? 90. Y'all with me? Let's go back for just a second and see what 90 is. Look at it. What's 90? TH is thorium. Y'all with me, folks? The uranium lost 2 pinkers, right? and became, remember, this is what determines what chemical it is, the number of these babies. And so it lost 2 of them and became thorium, which is also radioactive. Do you see where it says thorium-234? Why does it say 234 instead of 238? Because it lost 2 white ones and 2 red ones. Is that right? Yes. So the weight has gone down by 4, right? And thorium is, what does it shoot out? It shoots out one of these. Not very dangerous. Is that correct? Because it's so tiny. Not very dangerous. Tell me you're glad you know all this stuff. Could we teach this to 4th graders? And they would come home and blow you away with what they learned, right? Why don't you blow away a 4th grader with what you've learned, right? My granddaughter in the 7th grade called me the other day. She said, "Grandpa, I saw the nucleolus today in a microscope." This is 7th grade stuff, folks. Now, you remember the cell I put up there and that thing in the middle that's called the nucleus of the cell. I'm not talking about the nucleus of an atom now. And in that nucleus, there's another structure called the nucleolus. And this 7th grader, bless the hearts of the science teachers, helped her look in a microscope, and she was so excited. Of course, she knows what my world is. "Grandpa, I saw a nucleolus today." So you're as good as 7th graders, aren't you? Actually, sometimes I wonder about myself. So now there's another thing on this chart. By the way, what after all of these substances, which are all radioactive, finally get to the end, what is the end product? Lead. Don't you kind of know that? That given enough time, uranium becomes lead. Quite a long time. Let me tell you about this number here. This number is 4.5 billion years. I think you know that when there's a number up by the 10, it means that many zeros. 4.5 with 9 zeros is 4.5 billion. Are you all with me on that? Here's what this means. Every once in a while, the uranium shoots out an alpha particle, correct? It'll be 4.5 billion years before half the uranium is gone. It's changed into thorium or whatever else. Y'all with me? It's called the half-life. How many have ever heard the term half-life? See, most of you know about that. Even if you didn't know what that meant, I hope you can see what it is now. Scientists measure. I did this when I was a student in college taking physics. We measured the half-life of various radioactive substances. How long would it take before half of it is gone? What's the half-life of thorium-234? Only 24 days, less than a month, and half of it's gone. What's the half-life of protactinium? Just a minute or so. And then you go down, uranium-234, 10 to the 5th, that's 233,000 years. Notice down there, polonium, right there. What's the half-life? 0.00015 seconds. Is that very long? It's not. It's a 10,000th of a second. So once that's created, once that polonium is created because of this emitting stuff, it's gone in a few seconds. Half, right? And here's what my professor friend learned and began to study. He found out that beta particles, he found out that in granite rocks, if you look carefully, if you take a slice and look under a microscope, you will find places where there's a little bit of radioactivity there that is a beta emitter. And believe it or not, at a microscopic level, The beta can travel a little ways in the rock and stop. And when it stops, it does a little damage right there. And since there's some radioactivity there, it keeps sending out these beta particles, and it makes a little ring damage, a little line of damage that you can see under a microscope. When you cut it, actually, if you were looking at it from the side, you could see a shell of damage. Would that make sense? Because it's going in all directions. But when you slice it, you see the shell cut, or the ball cut, and there's a ring there. And they call that a halo. Now, what he found in granite was that these little radioactive spots, this is microscopic, but you can see the pictures. I'll show you the pictures, in fact. I think I can do that. Why is this thing? I guess it was earlier that I had his pictures. Yeah, there we go. And the next, I thought I put some pictures of the rings, but they're not there. So what you'll have to do is just, it's funny because, oh, there they are. There we go. Oh, there they are. Okay. Those are actual photographs through his microscope. Can you see the rings? Why are there multiple rings? Because the beta emitters, there are different chemicals there in that little radioactive spot, and some of the beta particles come out with more energy than others. So they go longer before they stop. Are y'all with me on this? And what he found in his research was that he could identify the places where the half-life was fractions of a second. And in some cases, maybe a minute or so. You can look this up actually all online. Just put his name, Robert Gentry, and you can read all of this stuff. And this was his position. In view of the fact that the scientific community believed, although it's never been shown or proved, that granite would form from a big molten mess, or a big molten volcano or something, and would take years and years, hundreds of years, thousands of years, maybe down deep where you can't lose much heat to form the granite. Are y'all with me on that? From a melt? Because those halos occur in such a fraction of time, and if it was liquid, the halo wouldn't occur. Y'all with me? This stuff is moving around. He said, this is a proof that the granite was created in an instant. Get it? What's the implication of that? There was a creator. Amazing. So the whole book, Creation's Tiny Mystery. These things are microscopic, but under the microscope you see the pictures. In fact, I think I had some more. Oh, that just shows you. See the U-238? I'll point at it. Can you see that says uranium-235? That particular ring is a beta emitter, and it came from that decay. We call this when an atom shoots something off and it becomes a different substance because it shot something off. We call it decay. I think that's kind of familiar with you. So he's showing you which rings came from which substance that shot off a beta particle. Got it? And he made the claim, he made the point that this proves, because these half-lives are so short, that this never could have formed from a melt because the radioactivity would be gone. Y'all with me on that? And when he wrote the book, he sent me a copy, a draft, asked me to proofread it, which I did. And if there was any suggestions, particularly, he wanted to know. And then it was published. And interestingly enough, Bob Gentry is like not a bull in a china closet, like a bull in a field that's going to do what needs to be done. And I didn't know that. When he was teaching me trigonometry and calculus, I just loved it. But somehow, and several years later, before I left college, he came to lecture about the halos, and I couldn't believe it. Some of our scientists from the university were there. It was a college in those days. And they were peppering him with questions, and there was tension. And I what's going on here? And it kind of is Bob's fault. Do you know anybody like that? Kind of difficult sometimes or something? I feel really bad about it because it caused people to criticize his work and to claim this and claim that and try to prove that it wasn't the case. By the way, can you see other ring effects out here? Can you see that? But I think that his work is a wonderful example, and I went through all of this effort to just give you another sense of how God created. He spake, and what does the Bible say? He spake, and it was done. If that wasn't the case, the halos wouldn't be there, correct? Because of the half-lives of some of the decay being so short, fractions of seconds. And so the stuff is gone before the granite is formed. Well, I didn't know that I went so long, so I'll quit and we'll start tomorrow evening. I hope I don't scare you away, but I hope you'll dream about pinks and whites tonight. So God bless you. Let's pray. Thank you again, Father, for the marvel of your hand, your creative hand. And I pray that you'd help us to grasp these things and maybe even be able to inform others of some things along these lines to help substantiate the idea that a creator made all of these things. We thank you, Lord, in Jesus' name. Amen.